Okay, so in this video, I want to discuss divergence theorem. And this is a topic from multivariable calculus. And this is the last and one of the most important theorems in multivariable calculus. And this theorem is really powerful. So first, I'm going to talk about a motivational example. I'm going to show you an example when we can apply divergence theorem. And then I'm going to actually prove, but I'm not going to prove it like really precise. I'm going to give you intuitional proof. What is the divergence theorem and why do we care about divergence theorem? So what is the statement of divergence theorem? So the statement is basically saying that if we given some surface S, so if S is a surface, and like for my example, because again, I'm talking like for particular example, so it's going to be example motivation for divergence theorem. And then let's take a surface to be a sphere, a unit sphere. A unit sphere. And for this surface, we also given a vector field. So first we're given a unit sphere, and my unit sphere looks something like this. And we also given a vector field F. So we're given a vector field F. And since we're like in 3D, then we have vector field F consists of three components. So my vector field F has components P, Q, and R. But again, like we're doing particular example, so my vector field will consist of the points X, Y, and Z. So for the given surface S, and for the given vector field, I want to compute a double integral. And what double integral do I want to compute? I want to compute the double integral over the surface S of F dot N ds. The name of this double integral is a surface integral over a vector function, and vector function in this case is my F. Or another name, I believe, for this integral is going to be just called a flux integral. Flux integral. Okay. So we want to compute this double integral. There's two approaches how we can compute this double integral. The first approach, we just thinking about this double integral as a surface integral. I mean, do computations that I'm going to show you in a second. But another approach to compute this double integral is apply divergence theorem. And what divergence theorem is telling me? So where can I write this down? I will erase this. So divergence theorem tells me if I have this integral on the left hand side, double integral over S F dot N ds, then this integral is going to be the same as a triple integral. But what is going to happen? Since we're given this vector field F, we're going to take the triple integral over some scalar function. And we're going to make the scalar function by taking the divergence of my vector field F. So it's going to be the divergence of F. And I'm taking the triple integral over some region in 3D. So in this case, my region is 3D. So if original S is a sphere, so this is my S, then the unit ball is going to be my V. And unit ball is a sphere with inside. So it's going to be the triple integral over V. And this is the divergence theorem. So from left-hand side, it's I have a double integral over a surface. From the right-hand side, I have a triple integral over some scalar function, which is in this case divergence. I'm going to discuss later what's the meaning of the divergence, and I'm going to discuss when I'm going to give you intuitional proof of the divergence theorem. So right now, I want to do two steps. For step number one, I want to compute the integral on the left-hand side. And so this is step one. And for step number two, I want to compute the integral on the right-hand side. And I want you to show that integral on the left-hand side equals to the integral on the right-hand side. Yeah, physics, yeah. And actually, intuitional proof I have read in physics book, which is called curl, divergence, and gradient, and all that nonsense. So if you really want to understand like this topic, I really recommend to read that book. That book is really good. Okay, so let's compute first integral on the left hand side. So let me erase. Yeah, I'm gonna. Let's actually say. So first I want to compute this integral. So I have the double integral over s of f dot n ds. Okay, so here's a couple of approaches how we can compute this integral. In my case, S is going to be just region which is described by x squared plus y squared plus z squared equals to 1. So this is a sphere, and my F is given by x, y, z, a vector field. So I'm not going to write down formula right away. I want to derive actually the formula. So what is n in this case? N is a normal vector of S. And if you're given some surface S, for example, in this case a sphere, how we can find the normal vector? I'm going to show you in a second. It's a normal vector. But if you have, normal vector of S. But if you're given a sphere, and this is our sphere S, and this sphere is given by equation x squared plus y squared plus z squared equals to 1, we all know how we can find this normal vector. We can think about the sphere as a level curve of a real valued function in terms of two variables. Or another way, what I'm talking about? If we will take this equation and move one to the left-hand side and set the whole thing to be equal to some function, so I will move it to the left-hand side, I will get equals to 0. So, and I will set left-hand side to be equal to the function, not use f, let's use g of x, y, z equals to what? X squared plus y squared plus z squared minus 1. Plus z squared minus 1. So I can see when g equals to 0, I will have a sphere with radius 1. When g will be equal to 3, I will have a sphere with radius 2. So this g is going to be kind of two-dimensional function. So for each g, I will get different spheres. And when g equals to minus 1, I will get just that. And then we know from here we can find our normal vector, because our normal vector is going to be just the gradient of this function. So we will have that normal vector is just equals to the gradient of g, because by definition gradient is perpendicular to level surface. Okay, no problem. But this is going to be a unit normal vector, so it's not only a normal, it's a unit normal. So I need to divide by the length of g. So in this case, let's find out what's my gradient of g. My gradient of g is going to be just a vector with 3 components when I take the partial derivative, so we'll have 2x, 2y, 2z. And if I will take the magnitude of this vector, let's compute it over here. Then I can see that my vector n then equals to gradient of g over the magnitude of gradient of g equals to 2x, 2y, 2z divided by the magnitude, and magnitude is just 4x squared plus 4y squared plus 4z squared. So 4 will be get factored, so it's going to be canceled out with this 2. And from this, I have the equation for my normal vector. So I can say that n is a unit normal vector in the following form, where n is equals to x, y, z divided by square root. So it's going to be n is equals to, and what can I do over here? I can factor my square root. So I will have 1 over square root of x squared plus y squared plus z squared with component x, y, z. Okay. So what I got over here? I got here my first part. I got what is my n. Let's try to move. Then, unfortunately, I don't have time to explain this video. My ds, let me erase this. My ds can be expanded by the formula. Actually, let me think. What should I do over here? How to introduce this naturally? So the first thing I can see is that if I will do the dot product of these two, I will get some scalar function over here. But I want to cancel out with ds, and ds is equals to, if I will write the partial derivatives, I don't want to, or okay, let's just find the dot product of these two. The dot product of f and n, I will give you x squared plus y squared plus z squared divided by square root. So we'll have x squared plus y squared plus z squared divided by square root of x squared plus y squared plus z squared. So from here, square root will get cancelled. I will have the square root of x squared plus y squared plus z squared. It's a result of the dot product of f and n. So I can rewrite the double integral as double integral over s of my function x squared plus y squared plus z squared ds. So here we can see how we started with the surface integral vector function, and we ended up with the surface integral over scalar function. And we know how to evaluate this integral. Evaluation of this integral is just using parameterization. And since S is the unit sphere, x squared plus y squared plus z squared equals to 1, I want to use a spherical parameterization. So in this case, I will get the use parameterization, use spherical parameterization. And what does it mean, like use spherical parameterization? I want to create a function Ru in terms of v. Then I will have my first component is cosine u sine v. My second component is sine u sine v. And my third component is cosine v. And this parameterization, I want to describe the whole function. No, not the whole function, the whole surface S. So in this case, if I want to describe this surface like a sphere, I can see that u responsible how the vector in xy plane is going to rotate. So this u is going to be this angle. So u changes from 0 to 2 pi because I want to rotate for a whole circle. And v changes is responsible as the angle between the axes. So this is my v angle. And we can see it's changes from 0 to pi, so v changes from 0 to pi. And I'm going to skip calculations. No, I'm not going to skip calculations. No, I'm going to skip calculations. So basically, by using this parameterization, how I'm going to write this integral. The first thing, I have my scalar functions. So instead of scalar function, I'll plug it in like x, y, and z. And ds is going to be equal to in the following form. So first, I have my part for my scalar function. And ds is going to be written as r of u cross r of v dA. When this part is well known like Jacobian. And we have done a lot of computation for spherical parameterization. So in this case, we can check that Ru cross R of V is going to be equals to just sine V. And the reason is why, because for spherical parameterization, you usually have like radius cosine U sine V, radius R like sine U sine V, and R cosine V. But since we only work on a boundary of a sphere, then my R equals to 1. And I know that Jacobian for change of variable from Cartesian coordinates into spherical coordinates is going to be R squared sine V. But since we work on only boundaries, R equals to 1. So this is going to be my Jacobian. So in this case, I can just rewrite this as a sine V. Thank you. Yeah. I'm trying to make my video accessible. I hope they're pretty accessible, but we will see. Yeah. Sine V, and instead of x, y, and z, I'm going to plug it in my parameterization, which is in this case, this is my x, this is my y, this is my z. So if I'm going to square them up, add them up, I will get that my original function will equals to 1. So I have just 1. So here I will have this function will become just equals to 1. And I will have sine v du dv. And for my bounds, I'm going to plug in by bounds for v. My v changes from 0 to pi, and my u changes from 0 to 2 pi. So we're going to end up with this integral. And this integral is really easy to compute. So what originally I'm doing? I want to show divergence theorem based on example, and then I want to give intuitional proof with divergence theorem. And divergence theorem basically says, write it down here, that if I have the double integral over s f dot n ds, it's going to be equal to the triple integral over the volume of divergence f dv. So right now I'm doing the first part, and my first goal is compute this integral and find the value of this integral. So this is over s. And then I want to find the value of this integral, 2. And I want to show that 1 equals to 2. So let's finish this computation over here. We can see that this function doesn't depend on u. So what I will get just 2 pi times the integral from 0 to pi of sine v dv. And in this case, this integral is equals to 2 pi of negative cosine, and negative cosine changes from 0 to pi. And you can easily check that negative cosine v, negative cosine pi is -1, negative will be positive. So these integrals will just be equals to 4 pi. Okay, so integral on the left-hand side will be just equals to 4 pi. Let's use like red one, 4 pi. Let's compute right now integral on the right-hand side and see what we will get. But before, let me just show you these computations. So we can see the integral on the left-hand side is pretty involved. We took the most simplest surface, which is a sphere, the most simplest vector field f, which was given by x, y, z, and this computation is really intense. And the beauty of the divergence theorem, let me show you computation for the integral on the right-hand side. And you will see that instead of doing all this algebra computation by using parameterization, figure out what is normal, and like just a lot of stuff, this integral is going to be way more easy to compute. Thank you. Okay, so let's here find this integral. So my next goal is I want to evaluate the integral, the triple integral over v of divergence f dv. So first, what is my f? My f is equals to x, y, and z. And if you don't know what is the definition of divergence, it's not a problem. I'm going to just show it right away. So divergence of f equals, if I'm giving my first component is p, my second component is q, my third component is r, the divergence of f is going to be just partial of p corresponding to x, plus partial of q corresponding to y, plus partial of r corresponding to z. And since I can see I have x, y, and z, then partial of x corresponding to x is 1, 1, 1. So divergence is going to be 1 plus 1 plus 1 equals to 3. And just I want to show like one cool thing. So far, I just written one line, and basically I already set up my integral. Because here, in order like to set up this part, I was doing a bunch of stuff which is already erased. But applying the divergence theorem, we don't need to compute double integral, just compute triple integral. And triple integrals here is going to be like super amazing. Why? Because divergence is super simple, it's equals to 3. So we'll have just the triple integral over 3 dv. Let me make it smaller, over v. But what is my v? My v is going to be just the volume of the unit sphere. It's here. And we all know that and we all know that the volume of the unit sphere is just equal to what? 4 pi over 3. So what I will get, I will factor first 3. I will have triple integral over v of dv. And the meaning of this integral is volume, because I have my scalar function is 1. So remember, if you have double integral of 1 is area, line integral of 1 is arc length, surface integral over 1 is a surface area, but in this case is a volume. So it equals to 3 times 4 pi over 3. 3 got cancelled, and I got 4 pi. And we got the same answer as I got answer over here for the double integral on the left-hand side. So triple integral on the right-hand side equals to the same value. And let's come back over here. So on the left-hand side, I have 4 pi. On the right-hand side, I also have 4 pi. And voila, not Green's theorem, divergence theorem in action. And let's summarize like this example. We were given as unit sphere a vector field f x, y, z, and I wanted to compute the flux integral over the surface of the sphere. So what I got? I can compute the integral on the left-hand side, the double integral, and you can have all this other computation. You got 4 pi. Or instead of computing this integral, we can just compute integral on the right-hand side. And in this case, computation is going to be really straightforward, and I will get the same answer. So it's equals to 4 pi. Okay, so I'm done with showing an example. Like, I don't know, do you have any questions or any comments? Like, word clear? Should be this one. Okay, so here I was done with computing actually the double integral, the triple integral, and showing that they're equals to each other. So let's discuss what is divergence theorem. What is the meaning of divergence theorem? So before we're going to discuss the meaning of divergence theorem, let's take a look at the integral left-hand side. And let's first discuss what is the meaning of this integral. So what is the best way to approach it? So let's consider the following problem. Let's say I have a pipe, water pipe, and for this water pipe, I have that my section, and this is section going to be section S. And the same as I have S over here. This is section S. And we know that if we have the section S, at every point, so this section S is going to be a plane. So at every point, I will get a normal vector n. Yeah, I'm doing it already, yeah. So this is n. So let's first, so we have like my S and I have my n. And let's discover this f. Let's take the most simplest f, and in this case, f is going to be the flow of the water. So at every point, I will just make my f to be constant and pointing to the same direction. So we can see, we can imagine like the water flows in this like water tube or like in this pipe, and we can see at this point, the vector, the normal vector, and the vector of my f are going to point the same direction, but they might have different length. So what is the meaning of this integral on the left-hand side? The meaning is I want to answer the question, how much water goes through this section S? And let me think how to say it. Like, I want to provide like kind of natural derivation of this one. So mass time. So this is my F. Okay, so amount of water is the speed. Okay, I can just describe like intuitionally. So the idea is the double integral over S ds, computing the area. So in this case, I will have the area of the circle. And the amount of water which comes through this surface area exactly going to be represented by F dot N. Why F dot N? Workshop. Okay, let's just try. I will try to do something. So I know that my mass is equals rho times V. Yes. If I will think about the V, so this is going to be my time delta T. And I want to find how much liquid goes through this S. So I want to find delta M over delta S, over delta T. And the mass that goes through this one, mass equals to density times area. Yes. And we are assuming the density is here is like constant. So what I have, area is going to be exactly like this circle, A. But amount, so this is V. So we have delta rho. So amount of water that I have in this tube for delta T time is going to be rho times A times delta T. Yes. And this is going to be the change of my mass. So if I want to find the change of my mass for some time, I will get it equals to rho A. So if we have rho delta V delta T. Okay. Yeah, I haven't prepared for this one, so I'm trying to. Okay, so let's just say you're gonna believe me that this is gonna measure the amount of the fluid that goes through the surface area. And the idea is that if you will think about this section as electromagnetic field, like so, this F is gonna be indicate not the water, but they're gonna indicate some, for example, like electrostatic field. And let's say they're gonna go and make some angle. So my electrostatic field is going to be also constant, but go this direction. So what I'm going to have instead of like this vector at this point, I will have these constant vectors. So I'm going to also measure the intensity, the amount of electric field that goes through my S, but I can see that my amount is not going to be full because if my electric field will go parallel to my S, then like there's going to be no electric field. For example, if I have that this is my S and this is my electromagnetic field, then no electromagnetic field comes through my S. So in this case, it means that my double integral of over S of F dot n ds going to be equals to 0. But if my electric field is going to be perpendicular. Oh, it doesn't see. It's going to be perpendicular to my section S. Then I will get the maximum amount of electromagnetic field that goes through my S. So that's why this is called flux. So it's basically what it does. It measures how much liquid goes through some surface by the given F, and F is describes the movement of this liquid. Yeah, I was trying to derive exactly and to show you the proof for this one, but unfortunately that failed. So I need to sit down and think carefully how to do it more precisely. Yeah, so this is the meaning of the flux. Okay. And right now let's show the proof of why is this double integral gonna equals to the triple integral of divergence V. So first we need to discuss what is divergence. And definition of the divergence that the following. Let's take, for example, like some sphere. And through this sphere, I have that some liquid, not liquid. Through the sphere goes goes vector field. And I want to measure how much arrows goes inside the sphere and how much arrow goes outside the sphere. So for example, this electric field behaves something like this. So this arrow is gonna goes inside the sphere, and this arrow goes outside the sphere. Is it not curly? It actually needs to be straight. Yes. So what I'm measuring how much liquid goes inside. But what if I want to answer how much liquid goes through this point? Or not like goes through this point, how much, because if you think this is as the flow, and we know we have kind of intensity of the flow, it's similar like if you go inside the river, you can feel divergence on yourself because divergence is going to be basically when like water is hitting you. And what we want to do if you want to compute the intensity or like the divergence at this point, we want to make my sphere smaller, smaller, and smaller until we reach the point. So, and what is the definition of this one? Because if I want, let's call this outside sphere S1 and this inside sphere, let's not name it first, then the amount of the fluid that goes through S1 is going to be the double integral of S1 F dot n ds. So what I'm going to do, I will take this like S R, when R is going to be radius of my sphere. So I can see when I will send R to 0, I will make the sphere be smaller and smaller, and for every R, I can compute separate integral. And in this case, I will be getting the integral of the flux. But the problem is going to be that when I'm sending my R to 0, I have my surface area over here, and I have liquid. So if you will try to compute this integral or compute this limit is going to be undefined. So how I'm going to help it out? Instead of taking like this integral, double integral over surface, I will divide this integral by the volume. And what I'm going to do, I'm going to take kind of the average. So I have some liquid goes through the sphere, but when I'm dividing by the volume of the sphere, I'm taking the average. I'm taking how much volume goes through each point. But it might be not uniform for different regions of the sphere. But if I will take right now this volume and send it to 0, I will find exactly the divergence of the point. So what I have that divergence of the vector field F. Let's write down it here. I have the divergence of F is going to be exactly the limit of delta V goes to 0 of the 1 over delta volume of the double integral of S F dot N ds. And this is the definition of divergence. And there is one derivation how we can show that this divergence is going to be actually equal to the partial first component of vector field plus x plus the partial of the second component corresponding to y and the partial of the third component corresponding to z. But this is different. But this is different story. So this is the definition of divergence. But right now, how is related to the triple integrals that we have over here. But right now, what can I do? I can take the sphere, and I can take, like, let's say, this small cube inside the sphere. And if I want to compute how much liquid goes through the sphere, I can put like a lot of small cubes inside my spheres, and I can measure how much liquid goes through each of this cube, and then I can add them up. But you can check if you will, you can see actually, if you will add this cube and another cube next to this one, say this one, then for this cube, you will have this this side. And if my vector field represented by this red line, and if I'm computing like how much vector field goes through this side, I can see that this cube, let's say cube 1, will constitute to the value with A. If I'm going to call A the amount of liquid that goes through the side, I will have positive A. But this cube, cube number 2, have the same phase, and corresponding to this phase for cube number 2, this will constitute with the value minus A. So you can see if you're adding 2 cubes next to each other, this side doesn't matter. So what can I do right now? I can fill in the whole sphere with all the different cubes, and what is going to be only important, going to be important like the sides, which is doesn't share that side with other cube. So the picture is going to be the following. So I have just a bunch of cubes inside my sphere. That looks something like this. So what I will have, I will keep this one. Let's write this down. So the amount of liquid that goes through, let's say, this cube 1, going to be represented by this. Let me think how I should say this correctly. Okay, so we take, let's name these cubes VI's. Then if you, and let's take we took n cubes, and we put n cubes inside my sphere. Then the total flux for this n cubes is going to be the sum from I equals to 1 to n of the double integral of vi of f dot n ds. Okay, so this is the amount of flux that goes to this m cube, but this doesn't equal to the amount of flux that goes through the sphere. It's just approximation of this one. So I will get exactly the amount of flux that goes through the sphere if I will send this n to infinity, if I will make my cubes to be smaller, smaller, and smaller. So if I'm sending n to infinity, I will get the double integral over s of f dot n ds. Okay, this is from one side, right-hand side. So by taking this flux, I will get the double integral. And this is the first part. This is the first part of divergence theorem, which is double integral over f dot n ds. So let's get this part. From here, I can see that this is my definition of divergence. Yes. So what can I do with this integral right now? I can divide by delta v and multiply by delta v. So this integral, so let's erase this a little bit and make it more compact. So we have here my vi 1 over delta v, limit delta v goes to 0, and this is my divergence f. Okay, I need this formula. So this integral is going to be equals to, if I will multiply and divide by v, I will have the sum from I equals to 1 to n, 1 over delta v of double integral of vi f dot n ds multiplied by delta v. Okay, so and actually I'm going to teach my own class over summer, so this is video kind of making to prepare myself because I haven't talked about this topic before, so I believe it's going to be a good way of practicing. And also for you guys, if you're watching, it's going to be you're going to just learn something new, or I don't know, just give me comments. Okay, so I'll have this one, but this is exactly is by definition of divergence is going to be divergence of f. So what do I have over here? I have here that the sum from I equals to 1 to n of divergence of f delta v. So from one side, I have this integral, this sum. From other side, I have this sum. So when I'm sending my n to infinity, when I'm making my cube smaller and smaller and smaller, I will get the total flux over my surface. So in this case, I have this double. In this case, according to the divergence theorem, I have the integral on the left-hand side. This is my first time when I'm doing live stream corresponding to divergence and flux integral. The reason is why I'm teaching. I'm not like professor now. I'm just a TA. So my students are going to have finals. So I just want to show them a couple of examples. But goal for myself, I'm going to teach my own class over summer. It's going to be like 8 weeks. And Math 53 is a little bit difficult to teach. So I want to use maybe like some streams on Sunday when I'm going to practice in some topics and people just can watch me practicing, talking about math, and you can ask me questions if you want. Because one way when you learn math by yourself, just sitting there, solving some problems, proving some theorems. Another way when you learn some math and you try to talk to people and explain some topic like to other. And I believe the second method is better because when you trying to teach someone else, at the same time you teach yourself. So this is super cool. Okay, so we have like these two sums and they're equivalent. For first time when I make my cubes smaller and I make put more cubes in my sphere, I will get flux integral. But what will happen with this sum? If I'm going to send my n to infinity and my q's will be smaller and smaller, we can see this delta v will become dv, and here I'm taking the integral over the volume because I was dividing here by volume. So what I will get because of this dv, I will get the triple integral. But when I send my n to infinity, I will get the volume of a sphere. So I will fill in the sphere fully. So I will have this v. So I will have the triple integral over v. But nothing will change with my function divergence. So I will get this divergence of f. And this is going to be dv. And we are done. And this is divergence theorem. So we can see on the left-hand side, by doing this procedure, we have double integral over surface bound over a surface of surface integral over vector field. But on the left-hand side, I have the triple integral over a scalar function of divergence of my vector field. And this was kind of intuitional proof that I can introduce in class to students why this formula is true. Okay. Yeah, I was forgetting and kind of just, it's already like 9 p.m. or something. Why is the amount of liquid that goes through this section S is going to be equals to F dot N? How did they derive it? I don't remember. And sometimes when you talk about some topic, if you don't know or forgot something, you can just freeze and your brain is just going to shut down. Okay. Okay, it's already 48 minutes straight. So that's it about divergence theorem and flux integral. This theorem is really powerful. So basically, the application from physics, or not application from physics. If you, the meaning of this one, can explain intuition of divergence of F. Yeah, I can do it. So integral on the left-hand side measures how much liquid goes through your sphere S. But integral on the right-hand side measures the volume of your sphere. But you take in the volume of some function divergence f. And divergence f, as we talked before, we can think about as an intensity of the vector field at some point of x, y, z. So, like the physics meaning of this integral is this: measuring the amount of liquid that goes through some closed surface, it's equivalent to measure the intensity of that vector field at every point enclosed by the surface. 2D example of this one. If you have some particle that goes on the boundary of a circle, and what you can do, if you have over here the lines of electric field, let's say like E. Then for physics, you know, when you have particles that goes around the circle, you will have some work done W. And this integral is going to be equals to exactly the line integral over C, when C is this path of my line of of E dot dr. And meaning of this integral is exactly the work done if it goes around this path. But this integral kind of two diversion of divergence theorem is the line integral over C of E dr. And let's say in this case, I'm giving like my circle, which is over there in xy plane. So my vector field E consists of two components, P and Q. then this double line integral over C of E dot dr is going to be equals to, by like kind of two-dimensional version of the divergence theorem called Green's theorem, the double integral over D, when D is going to be the area enclosed by this circle, of partial of Q corresponding to X minus partial of P corresponding to Y dA. So again, like measuring the work done going around the boundary is the same as double integral over the area. And what does it mean? I like to think about this as the work done when you go on a closed path, it's equivalent of the energy enclosed inside this region. So you can, when your particle goes around the circle, it's enclosing some kind of closed region. And this region, you can see at every point here, I have the lines of the electric field. I have electric field lines that go through this point. So I have kind of intensity of electric field at this point. But when you have intensity, like you kind of have enclosed energy over there. And this is the meaning of 2D version of divergence theorem. Okay, so I'm done for today, and it was like 52 minutes. I hope for someone it was useful, talking about derivation of divergence theorem. So thank you for watching, and see you later.